Video is on a different definition of acids and bases. The original definition, which is acids make positive ions, hydroniums in water, and bases put hydroxides in water as their only negative ion, that's Arrhenius, and that's what the other video was on. Bronstaed Lowry has a different definition of acids and bases, and it's basically based upon what they do when they react with water, or what they do when they react with other substances, such as when acids react with bases. Now, there's one key thing here. Bronstaed Lowry says that acids are proton donors, and that bases are proton acceptors. Well, where are the protons? Well, it has to do with an understanding of what a hydrogen ion actually is. Now, if you look up hydrogen on the reference table and you look at its average atomic mass, the average atomic mass of hydrogen is 1.0079 something. And what that means is while there are some atoms of hydrogen that weigh 2 or that weigh 3, the vast majority of them weigh 1. So the mass number, or the weight of the nucleus of most hydrogen atoms, is 1. Now, we already know that hydrogen always has 1 proton in its nucleus. Now, for those who don't remember, when you take the number down here, which is the atomic number, and subtract it from the mass number, right, that used to give us, right, that would give us a number of neutrons. Well, I got news for you. 1 minus 1 is 0. So most hydrogen atoms have 0 neutrons. Now, a regular atom that's neutral, right, I just erased the +1 sign. A regular hydrogen atom would have 1 electron as well to balance out its 1 proton, making neutral. But because hydrogen ions are +1, they have 1 less electron than they have protons. So they don't have an electron. They have 0 electrons. So essentially, most hydrogen ions, or hydroniums, okay, that attach to water molecules, are just protons. And so you can view acid-base chemistry as basically an exchange of hydrogen ions, which are protons. Acids are proton donors. So look here, what we have here is we have this acid. This is nitrous acid. And we have nitrous acid reacting with water. Well, why is nitrous acid an acid? Well, when it gets with the water, it donates its proton, which means it gives, you can think of this acid as being made of an H plus and a nitrite ion. All right? And so what ends up happening here, the H plus, which is this is the proton right here, gets donated. And what does donate mean? Well, when I donate something, I give it away, right? If I donate some clothes to the Salvation Army, they have my clothes, and I don't have those clothes anymore. Okay? When the nitrous acid donates its hydrogen or its proton, it doesn't have anymore. It turns into an NO2 minus 1. And the water here, interesting enough, is acting as the acceptor. Okay? So this is turning into this. But as it's doing this, it's giving its H plus to the water, and so the water ends up becoming H3O plus. This might seem repetitive, but the reality is you can view these, this is a reversible reaction. So what they say is these things come in pairs. So you can look at this from the other direction. Like if I put nitrites into a solution that contains hydronium molecules, the nitrites will take back some of the H's, like so, and the H3O pluses will turn back into the waters. And I'm going to put a double arrow indicating these are reversible. Now, all Bronstaed Lowry acid-base reactions happen what they call conjugate acid-base pairs. I'll put that down. Conjugate pairs. Now, what you're supposed to see when you look at these equations is that these two right here are a pair. A pair differs by a single hydrogen. So an HNO2 has 1 more hydronium than the nitrite ion. And the other pair that you see here, okay, are these two. And of those pairs, one is the acid and one is the base. Now, I'm going to use the second equation here. And I'm going to start with this. This NO2 is taking back the hydrogen. So this NO2 is acting as the base. In the other direction, the HNO2 is turning into NO2, so it's losing its H. So this is the acid. Now here's the easy part. Okay, if you can match up the pairs, the one that has an extra H is always going to be the acid, and the one with one less H is always going to be the base, right? So on the left-hand side, this H3O plus, which has 1 more hydrogen, is the acid, and that makes sense because it's turning into H2O. It's losing its H. It's donating it. So H2O is the base. Let's try another example. Here we go. So here's NH3, a nitrogenous base reacting with water, correct? All right. We know it's a base because it's in the base table. And it's defined as a base according to range because what it does in water. But you can also see how Bronstaed Lowry's definition works as well, right? Because the NH3 is going to essentially take the H plus off of the water and it's going to turn into NH4 plus. Now here's our pair right here, right? The reason why this is a base is because the reason why this is a base according to Bronstaed Lowry is not because of the hydroxides that are going into the water. It's the base because it's turning into NH4 plus. It's accepting the proton. It's getting an extra H. All right. The H2O is going to then lose that H, which means it's going to turn to OH minus, right? And so now you've got the two different pairs right here. And what you can see is if this is the base, then the other thing is the acid. And notice NH4 plus, the ammonium ion, has one more hydrogen, right? In the other conjugate acid-base pair, we have H2O and OH minus. In this case, the H2O is acting as the acid because it's donating its H, becoming OH minus, which is the base. Now, in the reverse reaction, right, the reason why this is the acid is the NH4 is turning into NH3. It's donating in the opposite direction. So the thing that accepts the hydrogen in one direction, its conjugate is going to be the thing that gives it back, okay, in the reverse reaction. Now, there's a term here that won't show up in the regions, but I'm going to mention it now because I might use it while I'm going through this. It's called amphoteric or amphiprotic. I like the second one better, okay, because it's an easy term to break down, okay. The word amphi is like amphibian. What do amphibians do? They live on the land and the water. They can do two different things, okay. And an amphibious vehicle is like those don't they have those duck buses in Boston that go into the harbor? You know, they have wheels on them, but they're boats too. So they do two things, right? An amphiprotic thing is something that can act as an acid and as a base. And if you go back to the last page, you'll notice something. The water in the previous example was acting as the base, right? This was the base. The water was, here we go. The water was the base, right? And here, the water is acting as acid. So this is interesting. Some things can both accept hydrogens or lose them. Water is one of those. Water can turn into hydroxide when it reacts with a base, or can turn hydronium when it reacts with an acid. However, being a Bronstaed Lowry acid or base is not dependent upon the presence of water. So you can talk about how an acid and base react. Okay, so what I have at the bottom here is I got nitric acid, which is a strong acid, and I got the hydroxide. Now the hydroxide, I really would be reacting with the NaOH, but we consider the metal and the metal hydroxide to be what they call a spectator ion. It's not really involved in the reaction. It's not changing. So really, if you have an acid reacting with a base like sodium hydroxide, you might write the equation like this. And then you'd be like, oh, I get NaNO3, the salt, and the water. But most chemists would do this a different way. They would write it this way. See, they would consider that the sodium ions would be still dissolved in the water, still mixed in, and they really don't do anything or change, right? The only thing that you're making here is water. This is soluble. It's not precipitating out. So the real reaction, according to this, would be this. Let me do a quick erase here on this one. Zip, 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 zip. All right. Now, I'm also going to erase this up here and give us a little more space. All right, so what's the reaction going to be? Well, the HNO3 is going to react with the hydroxide to make water. So in this case, the acid is acting like an acid, and it's going to turn into the nitrate ion. It's a reversible reaction. And the hydroxide is going to act like the base. The pair for the HNO3 is the NO2 minus, and in the reverse reaction, it's going to take it back. So this is a base here, and the conjugate of the hydroxide here is the water, which means this is the acid. However, in reality, sometimes these things can happen in the absence of water, okay? And you won't necessarily make water when you have certain acids and certain bases reacting. So we're basically saying the thing that donates the proton, that's the acid. If that's the acid on one side, then its conjugate is the base on the other side. And if you've got one conjugate acid-base pair, right, you have a conjugate pair here, you know what the other conjugate pair is, and make sure you're aware the one that has the extra H is always the one that is the acid. So I've added one more page to this video, and on this page what I'm going to just do is I'm leaving two equations, and I'm not going to really say anything. I'm just going to label it. So what I would do is, if I were you, I'd pause for like a minute, and I will label it, and you can pause at this point and you can check that you know what you're doing, basically. So I've put my pairs in, and now I'm going to have you pause it again, and I'm going to label what's the acid and what's the base. But check the pairs are correct. And now I have also included the pairs, so you know that the one that's got the one extra hydrogen is the acid, and one with one less is the base. I hope that helps. And have a nice day.